A pushdown automaton, or PDA, is like a tiny robot that reads a word one letter at a time. Remember some things using a stack. Think of a stack of plates you can only add to or remove from the top, and decides whether the whole word is accepted or rejected. Formally, a PDA is a 7-tuple M equals open parenthesis Q comma sigma comma gamma comma delta comma Q sub 0 comma Z sub 0 comma F close parenthesis. Q is a set of states, the robot's moods, for example happy or waiting. Sigma is the input alphabet, the letters the robot can read such as a B, C. Gamma is the stack alphabet, the symbols that can appear on the plates like X, Y, Z. Delta is the transition function, the robot's rulebook that tells it what to do. Q sub 0 is the start state, where the robot begins. Z sub 0 is the initial stack symbol, the first plate placed on the stack, often a special bottom marker. F is the set of accepting states, the moods that mean the robot says yes. Visually imagine a hallway states with doors transitions. At each door there is a small table, the stack, where you can push a new plate, pop the top plate, or leave it unchanged. This combination of hallway navigation and stack manipulation gives the PD a extra memory beyond a plain finite automaton. Explanation: the transition function delta tells the PDA exactly how to move. It looks at three things at once: the current state, the next input symbol, or the empty word epsilon if it wants to move without reading, and the symbol on the top of the stack. Then it decides two things: which new state to go to and how to change the stack. Formally, delta Q cross, sigma union epsilon cross gamma to power set of Q cross gamma star. Input: a letter or nothing the robot reads. State: the robot's current mood. Stack symbol: the plate on the top of the stack. Result: a set of possible pairs left parenthesis Q prime comma gamma right parenthesis, where Q prime is the next state, and gamma is a string of stack symbols that replaces the top symbol, push, pop, or replace. For example, a rule like left parenthesis Q comma a comma X right parenthesis maps to left parenthesis P comma X, Y right parenthesis means if we are in state Q, C and A in the input, and X is on top, then go to state P and push a Y on top of X so the new top becomes Y. This is just like saying when you see a red ball input while holding a blue plate stack, put a green plate on top and walk to the kitchen new state. A PDA can say a word is accepted in two ways, just like a game can end either when you reach a special tile, or when your inventory becomes empty. By final state, the robot finishes reading the whole input and lands on a state that belongs to the accepting set F. Think of a maze where the exit is a highlighted room. If you step into that room after using all the clues, you win. The stack may still have plates left, but it does not matter. By empty stack, the robot finishes reading the input and empties its stack except for the bottom marker. This is like a chef who must use up all ingredients before the dish is complete. Even if the robot's mood state is not special, the empty plate pile says the word is accepted. Some textbooks also combine both criteria final state and empty stack. Both acceptance modes are equivalent in power. Any PD, a using one mode can be transformed into a PD, a using the other. These two views give flexibility in designing PDAs. Sometimes it is easier to empty the stack, sometimes it is simpler to aim for a final state. Explanation: to turn a context-free grammar CFG into a PDA, imagine the PDA as a storyteller that tries to rewrite the start symbol into the input word using the grammar's production rules. The construction works like this. 1. Start. Put the start variable s on the stack and begin in a single start state Q sub start. 2. Reading productions. Whenever the top of the stack is a variable a and the PDA is not reading any input symbol, uses epsilon moves, it can replace a by the right-hand side of any production a goes to alpha. This is done by popping a and pushing the symbols of alpha in reverse order so the leftmost appears on top. 3. Matching terminals. When the top of the stack is a terminal symbol that matches the next input symbol, the PDA reads a from the input and pops a from the stack. 4. Except, after the whole input is consumed, the stack should be empty, or the PDA can go to a final state. If this happens, the input is derived from S using the grammar, so the PDA accepts. Real-world analogy. Think of a chef, the PDA, who has a recipe, the grammar. He starts with the dish name start symbol on a sticky note, the stack. He repeatedly looks up how to make each ingredient, production rules, and writes the sub-ingredients on new sticky notes, replacing the old one. When a sticky note says tomato, a terminal, and he actually sees a tomato in the pantry input, he uses it and removes the note. If the pantry is empty and all notes are used, the dish is ready, the word is accepted. Mathematically, the constructed PDAM equals open parenthesis curly q close curly sigma gamma delta q s empty set close parenthesis where gamma equals v union sigma variables plus terminals and delta contains dash open parenthesis q comma epsilon comma a close parenthesis goes to open parenthesis q comma alpha close parenthesis for each production A goes to alpha. Dash open parenthesis q comma a close parenthesis goes to open parenthesis q comma epsilon close parenthesis for each terminal A in sigma. This PDA accepts exactly the language generated by the CFG. Explanation: a deterministic PDA (DPDA) is like a robot that never has to guess. At each step there is at most one possible rule to follow. Formally, a DPDA's transition function must satisfy two conditions. For any state q, input symbol or epsilon and top stack symbol x, there is at most one pair q prime gamma in delta of q, a x, and if an epsilon move exists, no other move that reads a real input symbol may exist for the same stack top. This restriction makes DPDAs weaker. They can recognize only the deterministic context-free languages, DCFL, a proper subset of all CFLs. For example, the language A to the n b to the n, where n is greater than or equal to 0, is deterministic and can be recognized by a DPDA. A non-deterministic PDA and PDA can choose among many possible moves, like a superhero who can take any of several parallel paths. This extra freedom lets it recognize all context-free languages. A classic example is the language A to the nb to the mc to the n plus m, where n, m are greater than or equal to 0, which needs non-determinism to decide when to switch from pushing A's to pushing B's. In summary, DPDA is a strict subset of NPDA. DPDA languages equal DCFL, which is a subset of CFL. NPDA languages equal CFL. Understanding the gap helps compiler designers know when a grammar can be parsed with a simple deterministic algorithm, LL1 or LR0, and when more powerful techniques, LR1, LA, are needed. Components, states, Q push reading A's, Q pop reading B's, and Q accept. Stack alphabet, Z0 and X, where Z0 is the bottom marker and X represents one we have seen. Start state, Q push with stack top Z0. Rule 1, while in Q push and seeing an A with any top symbol Y, either Z0 or X, push an X, add a plate for each A. Rule 2, when the first B appears, switch to Q pop without reading a new input, an epsilon move, as long as the top symbol is X. Rule 3, in Q pop for each B read pop 1X. Rule 4, when the input is finished and the stack top is the bottom marker Z0, move to Q accept via an epsilon move. Rule 5, Q accept is the only accepting state. How it works: the PDA reads A's, stacking an X for each A like counting with plates. When the first B arrives, it stops stacking and starts popping 1X for each B, ensuring the numbers match. If it finishes the input exactly when the stack returns to the bottom marker, it moves to the accepting state. If there are extra A's or B's, the stack will not be empty at the right time and the PDA rejects. This example mirrors a child counting 1, 2, 3 while putting toys on a shelf, then taking them off in the same order when the game ends. The numbers must match for the game to be a success. The equivalence between PDAs and context-free grammars means that for every PDA there is a CFG that generates exactly the same language and vice versa. The two directions are : 1 from CFG to PDA described earlier. Replace each production A arrow alpha by a rule that pops A and pushes alpha on the stack. Match terminals with input symbols. This construction guarantees that any derivation in the grammar corresponds to a stack manipulation sequence in the PDA, so the languages are identical. 2. From PDA to CFG, the more subtle direction. Given a PDA M equals open parenthesis Q comma sigma comma gamma comma delta comma Q sub 0 comma Z sub 0 comma F close parenthesis, we build a grammar where each variable is of the form open bracket PXQ close bracket, meaning the PDA can go from state P to state Q while popping the stack symbol X and possibly pushing others, and reading some substring of the input. The production rules are dash for each transition open parenthesis p, comma a comma x close parenthesis arrow open parenthesis r comma gamma close parenthesis, where gamma equals y sub 1 y sub 2 ellipsis y sub k with k greater than or equal to 0. Add open bracket p x q close bracket, arrow a open bracket r y1 s1 close bracket open bracket, s1 y2 s2 close bracket open bracket, s sub k minus 1 ykq close bracket for all intermediate states si. If gamma equals epsilon meaning pop only, add open bracket pxq close bracket arrow a when the move reads a or epsilon if it is an epsilon move. For each accepting state f in f, add a start rule s arrow open bracket q sub 0 z sub 0 f close bracket. The intuition, a variable open bracket pxq close bracket records a possible segment of the PDA's computation that starts with x on the stack, begins in state p, ends in state q, and consumes a substring of the input. By chaining such segments, we can describe any full accepting run. Proof sketch show that any string derivable from S corresponds to a sequence of moves that leads from the start configuration open parenthesis q sub 0, w, z sub 0 close parenthesis to an accepting configuration. And conversely, any accepting computation can be broken into segments that match the grammar's variables. Thus, the languages are equal. This bidirectional conversion proves that PDAs and CFGs have exactly the same expressive power. They both characterize the class of context-free languages. The construction also gives a practical method. Given a PDA often derived from a parsing algorithm, we can automatically write a grammar that a compiler writer can inspect and modify. In compilers, a PDA is the engine behind syntax analysis, also called parsing. The source program is a long string of tokens such as identifiers, symbols, and keywords. The parser must check whether this string fits the language's grammar. LL parsers, which are top-down, simulate a deterministic PDA that reads the input from left to right and expands the start symbol using leftmost derivations. The PDA's stack holds the grammar symbols that still need to be matched. At each step, the parser looks at the next input token, the look ahead, and decides which production to use. If the grammar is LL1, meaning the decision can be made with a single look-ahead token, the PDA is deterministic, and the parser runs in linear time. LR parsers, which are bottom-up, simulate a deterministic PDA that also reads left to right, but builds a rightmost derivation in reverse. The stack contains states that encode how much of the input has been reduced to grammar symbols. When the parser sees a token, it either shifts, pushing the token or state onto the stack, or reduces, popping symbols that correspond to the right-hand side of a production and pushing the left-hand side. LR1, LA, LR1, and SLR1 are common deterministic PDA-based parsers used in tools like Yak or Bison. Real-world analogy: imagine parsing as assembling a jigsaw puzzle. An LL parser looks at the picture on the box, the grammar, and tries to place pieces starting from the outer border, which is top-down. An LR parser first piles up pieces, shifting them, and whenever a recognizable pattern appears, it glues them together, reducing. Both approaches need a stack. LL keeps track of which picture parts are still missing, while LR keeps track of which partial pictures have been formed. Because PDAs can be deterministic for many practical programming language grammars, compilers can implement fast single-pass parsers. When a grammar is not deterministic, compiler designers either rewrite the grammar to fit a deterministic PDA, sometimes by factoring or eliminating left recursion, or they resort to more powerful parsing strategies such as generalized LR, which uses non-deterministic PDA techniques and still guarantee correct syntax analysis. Thus, PDAs are not just theoretical toys. They are the conceptual backbone of the parsing algorithms that turn human-written code into machine-understandable structures.